can't get more energy out than you put in.
The PV cooling people, we are living proof of Finn Staple. There ain't no such thing as free lunch. And yet, thermodynamics is a harsh mistress. Our goals: define what the effects of PV heat loss, explore real-world options of cooling PV arrays that others have tried, seek out the advantages, disadvantages of each type of cooling system, evaluate the cooling system as a dump load, survey our existing planned expansion of the demonstration trailer, and decide on a practical cooling option. So we are also in the setting up a real-world cooling system that demonstrates the effects of cooling on at least one of our PV. Everybody rates their panels at 25 degrees C, 77 degrees Fahrenheit. That's standard normal temperature for these. This is what happens to a PV cell in the upper left-hand corner. And I'm trying to find a little laser.
It's a little red thing.
Little red thing. Right here. This is a typical PV panel. This is without cooling, the red, and you can see that as it goes up, the efficiency drops pretty drastically. With cooling, it stays usually around 10.5 to anywhere to 13% more efficient. And how much it's going to change it? Well, our math worked out for a Sharp solar panel, 0.485 per degree Celsius. Our SunForce 37 models do not list a temperature coefficient, which really was not really. But it is a crystalline poly cell, so we can rough out it because a single cell in a crystalline structure, it's approximately negative 2.25 millivolts per cell, and at all given temperatures, and that's from our Dunlop book. So for our polycrystalline PV panels, taking the numbers that we're going to see about 0.12 volts per degree Celsius for the entire array for the panels. And a charge controller, if we don't arrest it, a charge controller is going to reach voltage minimum, it stops charging. So what we decided that we would try to do then, thinking it's got to be as simple and reliable as possible. Have a feedback loop for positive control. And so that's where our basic started. What were our cooling options in our research? Three real-world options exist. Number one is liquid cooling. And that can be any kind of liquid. The two most common liquids, I surprisingly found a system where they were dumping essentially antifreeze on it, which is like, wow, really? And all the cats in the neighborhood will come and visit you. There's also water used. Air cooling has been tested. University of Singapore spent quite a bit of time doing it. And there are a couple hybrid systems. Under a certain degree temperatures, they use air. Over a certain degree temperature, they use water. We took a look at liquid. More efficient water has a high heat capacity. It's 1 calorie per gram centigrade, 4.81 joule per gram. It's stable, it gives good contact service, it's used for a dump load. Evaporative open loop system is the first type that we found in the research, and then we found a closed loop and an exchange, and it can be coupled with geothermal. You can actually take that water that you run down, run it into a geothermal loop, and store the energy. So it's pretty much there. It's a simple system. It has a collection gutter, a sprinkler head, water storage, and a pump. That's it. You can put all kinds of people. They actually have, University of Singapore had a really cool little piece of what requires sensors, timers, pump controls to ensure that the system does not use the power generated. Heat exchange for domestic consumption if chosen will also use power and pumping fluids and heat exchangers, and that's adding again to the amount of energy that you're going to use. Closed loop system, really cool. We spent a lot of time actually trying to look at this.
Trying to make this work.
Yeah, trying to make this one work. It has a heat exchange panel. It's a closed loop. As you can see over here, there's no fluids exposed to the atmosphere. There's a heat exchange / storage tank, and then it's very, very commonly used for domestic hot water or a geothermal sink. There we go. The roll-on, this is a refrigerator back that's been modified to set on a solar panel.
Yeah, there's a company in Italy that is now making and manufacturing these specifically for solar panels. $60 for one panel. Just
back,
for the
a
cooling.
heat sink for a back
Do you
panel.
know, like, how big is that exchanger right there?
That one's made for a standard size panel, so like it's 30, what is that, 30?
It was 30.
36 by
36.
60 or something.
Yeah, 36 by 60. So they're really cool, they stick right back on the panel.
It's really nice.
And we tried to find roll bond anywhere, and I even like called the roll bond factory, and they're like, nope, we won't make one of those for you because we have to engineer it and set it up. That's why we moved our company to Italy. They're doing the solar dump load, can use water glycol, doesn't matter, it's closed loop. Water glycol has a higher heat capacity than air, freezes lower temperatures, so it's cold weather friendly. System is still relatively simple. It has demonstrated history, and it can be coupled with geothermal again and domestic heat. The domestic heat is a big one. Disadvantages though, will corrode the system and components. There is a lifespan to them. There's a number of pump hours on even roll-on. The weight of exhaust in our trailer, heat recovered from a water geothermal, no space in our little trailer to store it at this point. No exchange to heat panels that can only be cooled to the end. If there's no way to exchange that heat, again, we're back to where we were at with water. You can only cool it so far. Cool it to the and ensure the system does not use all of the power generated. All of the systems that we looked at, they had a pretty, they had incredible mathematical models of how exactly long they're going to cool it, so that the panels would decool, they'd warm up slowly, and then they time it to pump the next cycle on, so that they're not using all the power. But yeah, I mean, they really spent a lot of time. Heat exchange for domestic consumption have chosen walls. Then the last thing we looked at, forced air. Can be relatively self-contained, though air has a lower heat capacity, is still an effective coolant. The HGTO, et cetera, the folks that we were looking at University of Singapore, show that a crystalline panel has an exchange flow rate of about 0.055 kilograms per second of air on the back of a panel. It will keep it at a steady temperature. And if you overblow it past that, it still cools at the same rate. As the heat goes up, it still has a positive effect because it's not storing that energy anywhere, it's essentially evacuating it. Can have an effective feedback loop, either electromechanical or fully electronic temperature systems. Can be made pretty much with off-the-shelf parts that the COT owns, so we chose to do that. This is basically a schematic of it. They had an AC and a DC blower to do their experiment. We just have, of course, a DC blower. So the disadvantage of it, again, airflow has to have a fairly high rate. Manifold must flow at a rate beyond 0.055 kilograms per second. Otherwise, it will not cool at that constant value. It does require sensors and control to ensure the system does not use all the power generated. Heat exchange for domestic consumption, again, it would be difficult. You really, if you're going to blow the hot air into a building, it would require ducting and all of that. So we went to the trade.
I mean, we decided with the air because it's lighter, it was cheaper, easier, can be used as a dump load as well, and it fits in the trailer a lot better. We found mostly, I'd say, all the parts here in, like, we used all parts from the classroom. So
we in our design, we decided that we were going to mount it on the back of the panel, obviously, and we scoured around in Wally's junk pile and found some 12-volt fans. Well, we're on 24 volts, so we just came up with a really simple circuit. 100 ohm watt, 4-watt resistor puts it down to 12 watts from 24. We taped it back to the existing panels, and it's really relatively non-destructive. You can remove the panels. The way we designed them, you actually just Gorilla Tape or duct tape them onto the back of the panel, and you can move them around. We designed a simple little spreadsheet to access what flat fan flow we would need to reach that 0.055. So all the fans that we're using are rated at 38.4 CFM to saturate cooling beyond 0.55 kilograms. You look at the math there, it converts the CFM to meters, and down, and it basically means that our fans are producing 0.213. So how many fans do we need? Just create a little simple logic thing here. You put the number in there, and you take your best educated guess, and it would pop up either good to go or no go. It ends up that we have to use 3 fans to reach the 0.64 kilograms per second.
We made a panel for each 2 panels for the gate. We did not make cooling for up on the roof, just the gate panel, which was easier to install. And for the past few days and the results, they significantly cooled the panels. Boom, here we go.
The uncooled PV on the left, right there, it's kind of hard to see the numbers, but we saw significant voltage drops, especially as we got into the 50-minute, these is 10, 20, 30, 40, 50. We start seeing our voltage drop. We're on the cooled panels, we're getting 20.2. On the uncooled, it's 19.5. It consistently showed degradation over time. We kept going. We had insulation problems, as you know, in the last 2 days. The sun doesn't like to shine. So
Shine
the panels
through in the middle.
yeah, right. It's like whatever. So we ended up, but with the test, it definitely showed that it positively cools it. And there we are doing the, we tested on a larger prototype panel. It was proven.
That's just a geothermal camera that I'm using to test how hot the actual panel is, how much temperature is gained.
It was 12 degrees cooler after 10 minutes of fan run. The actual panel surface on the front and the back cooled 12 degrees. So, and the draw is 8.64 watt at 0.26 amps, which runs out to be, I did the math here, it's actually like, what is it, 6.006, no, well, totally, with 2 fans running, we're running at 14.4% of our total power that we're creating. We're using 14.4 to cool it. And we're actually, you would have lost more, you would have lost like 17 something in PV if without it. So we gained 3%.
And I was assigned with the AutoCAD task, and I, just like Corey, had no idea what I was doing. So this took me a few days to do. It's just a very basic, simple design, but AutoCAD is tricky. So I had help from Corey, and I had some graphic design friends that helped me along the way too. Obviously, it's not a house, but it's, you know, something right there, that's for sure. And those little CPU fans, I actually found there's a website called GrabCAD, and there's engineers and designers that they design their own things, and then they'll upload them onto a website. You can use them for your projects as well. You can go on to the next one. That's just me sitting away there. And this is actually, then we turned the AutoCAD file into an STL file, and we brought it over to Montech to 3D print. And I got this little 3D print job. It's just a small little, scaled down to about, what do we do, Corey, 1/10? Yeah. Okay, so that's pretty accurate to scale. And this is just the inside of the printer as it's printing, which is, it's pretty cool to watch. It's kind of a bad picture, but it shows a little bit of it. Yeah, and that's it right there up close. Just those little fans on the panel. And that's, we just did the panel, our panel that we attached to the PV panels. I didn't design any PV panels.
Those little bearings in there work, right?
Yeah, the little bangs in there work great.
They might have had I made it a little bit
If you
bigger.
blow really hard.
Yeah.
So in conclusion, the final product, we manufactured 2 cooling panels, a PV gate on the trailer, installed them, and complete with a thermostat. It's not on this picture, but it's on the left-hand panel. We went really simple. We just went with a bimetallic switch so that there's no electronics that we have to maintain. It's set at 77 degrees, so once it reaches past standard temperature, the fans can kick on. And
Once it falls back below 77, they'll turn
once it
off.
falls below 77, they fall off. So in the last couple of days, all we had to do is let the rain take care of the cooling. And it's really, we had our own water cooling system. It's been tested, functionality, it works as designed. Turns on at 77, it went, clouds covered it up. Went under 77, it shut itself off. So it's there and it's operational. And it's been much better buttoned up than
Rolled on for solar panels.
and they're probably going to come down in price here in the U.S.